Here's an example of the type of problem where Green's theorem is very handy. This problem says, let's calculate the line integral of this vector field, f of xy is equal to cos x comma x, around the boundary of the rectangle. 0 is less than or equal to x, 0 is less than or equal to 2, and 0 is less than or equal to y, less than or equal to 1, oriented counterclockwise. I've kind of drawn a picture of this region at the left here. Here's the problem with doing this as a line integral. Because this is a line integral, this boundary is the boundary of a rectangle, and it has 4 sides. If we're going to do this line integral, we have to do the line integral over this left-hand edge, this bottom edge, this right-hand edge, and this top edge, and we have to add those contributions up. So for example, we would need to say, okay, let's calculate the line integral for the right-hand edge. The line integral for the right-hand edge would say, well, first, let's write down a parameterization. The parameterization would say x is equal to 2 and y is equal to t as t goes between 0 and 1. That gives us a parameterized curve that goes along the right-hand edge. Then I would calculate dx and dy like so. And then I would write down the line integral of f ds. That would be the integral of cos x dx plus x dy. So I'm sorry, dy is equal to dt. Since x is equal to 2, that becomes the integral of 2 dt from 0 to 1, and that gives us 2. And so this line integral along the right-hand edge would just be 2. That's fine. That line integral wasn't bad, but that's 1/4 of the problem. Then we would have to do the one along the top, the one along the left-hand edge, and the one along the bottom, and add all 4 of those line integrals up. Some of those line integrals are going to be harder or easier than others. So if we instead use Green's theorem, this says that we should instead calculate the double integral of the curl of this vector field. So if this vector field here, p is equal to cos x and q is equal to x squared, del q del x minus del p del y is what we integrate in Green's theorem. The derivative of p with respect to y is equal to 0, and the derivative of q with respect to x is 2x. So to calculate this with Green's theorem, we just calculate a double integral of 2 with respect to a, and we're calculating it over a very simple 2-dimensional region. It's a rectangle. And so we would get an integral. Well, we're calculating the double integral of 2x. And if we do it dx dy, x goes between 0 and 2, and y goes between 0 and 1. Now, it is a double integral, but it's a simple double integral where we just do it twice in a row. We don't have to parameterize 4 curves, and we don't get 4 different contributions to add up. And you can check that when we do this double integral, the answer is going to be 4 by just kind of evaluating this step by step. So in this case, because the vector field is or doing the line integral around the vector field takes so much more work, using Green's theorem and converting it into a double integral is a big win here for us. It gives us many fewer steps. And also, when we took these derivatives, it got rid of this trig function. So sometimes using Green's theorem can make your problem much easier to do the calculation for.